Okay, so we are back here continuing to talk about constrained diffusion. This is the third video in a series of videos going through and analyzing this model problem where we have diffusion happening between two infinite sinks. So the concentration of some chemical is held at 0 here, and then in between we have some initial concentration of a chemical, which we can make it as general as possible by calling it f of x. Across this medium here, the distance is L between them, and then we said we expect that there's some kind of solution that should look like this. So it starts at a constant concentration, then it dives down to 0 after we start it, and it's kind of steady, and then it gradually, all the mass exits, and it goes down to 0 as we approach infinity. And we're looking for an equation that will give us this behavior. And we said that Fick's second law is the equation that governs that, and then we needed two boundary conditions and an initial condition in order to solve that. In the last video, I went through and started from the math. Okay, so purely looking at math in that one, and we used a technique called separation of variables that you could use. We said maybe we're just going to guess that there's some function of x and a function of t that we multiply together that might work for that one. And we did some analysis, and it turned out that that we think that there should be a solution that looks something like this that will work. So the concentration is a sine lambda x plus b cosine lambda x e to the minus lambda squared t. And so this is our general solution. This will satisfy the governing partial differential equation, and now we need to figure out how to make this satisfy the initial and boundary conditions. So that's what I want to focus on here in this video. So let's start by just writing out briefly what that was. So we said our model problem again was dc by dt equals d squared c by dx squared. And then we said c at x equals 0 is 0, c at x equals L is equal to 0, and then c at t is equal to 0 is some function f of x. And then we might look specifically at the case where that's a constant of C0, but yeah. Anyway, so this is our model problem, and then we used separation of variables in the last video, and that told us then that the equation should be a sine lambda x plus b cosine lambda x times e to the minus lambda squared t. All right, so now we need to then, so this will work for that part, and now we need to make it work for these things. So we're going to start applying our conditions, and the easiest one to start with is this first boundary condition. So first boundary condition, c at x equals 0 is equal to, so if I put in 0, it's a times sine of 0 plus b times cosine of 0, and that's a 0, times e to the minus lambda squared t, that doesn't have an x in it. This should equal to 0. We need that to be true, and so sine of 0 is equal to 0, so that goes away, and e to the minus lambda squared t is never equal to 0. There's no way this could ever actually be equal to 0, and what that tells us then is that therefore b must equal to 0. So that's great, makes life a little easier. So we have three unknowns here, lambda, a, and b, and we've already figured out one of them without having to do any really elaborate algebra. So what does this leave us now? We'll go ahead and rewrite this again. So c of xt now we can say is equal to just a times sine of lambda x times e to the minus lambda squared t. Okay, Our function now must look like this. And so we have this equation done, and we've got this boundary condition. And next, we're going to try the second boundary condition. Second boundary condition. C at x equals L is equal to a sine lambda L. So if I put the L in for x, e to the minus lambda squared t, and that needs to be equal to 0. Okay, so we've got three things here multiplied by each other. We need one of them to be 0 to make this work. This is not 0 ever, no matter what we do. So this can't be 0. And if a were equal to 0, then we'd have a pretty boring solution. We just have 0. The whole function would become 0. And that's not very interesting, so can't be 0. Or we'll say it's boring. And so what does that mean? This must be 0. This sine term, okay? So sine of lambda L needs to be equal to 0. And it turns out that this is true for an infinite number of possible values of lambda, because if you recall, sine of x looks like a wave, right? And so it looks like this. Okay. And so it's got a 0 here, there, here. All these points are 0. All right. So sine of x is equal to 0 at x equals 0, at x is equal to pi, 2 pi, dot, 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 and negative pi, negative 2 pi, dot, dot, dot. Okay, so all integral multiples of pi. And so we might describe then the solution as, the solution is n times pi. Okay, so we can say that therefore we need lambda times L to equal to n pi for n is equal to 1, 2, 3, dot, dot, dot. The negative, so sine functions have a property that the sine of negative x is equal to negative sine of x. So it turns out that the negative solutions are not linearly independent. Note negative solutions are not, or are products, or is another way to say it, are products of the positive ones. Since sine of negative x is equal to a negative sine x. So this means that if n is negative 1, it's really n of 1 just times the negative, which is a constant. Okay, so it turns out that we can capture all the possibilities here with just the positive ones. And again, the 0 doesn't really mean anything in this case. So this makes things very tricky because it turns out that there are, so therefore there are an infinite number of linearly independent functions that satisfy this boundary condition. So that makes things seem a little messy, right? But they all need to be of this form. So we can say that lambda equals n pi over L. And remember that this lambda is this constant in here in our equation like this, and it's also up here in the exponent. But so then we can say that C of xt is equal to so we have to sum up all the possible values of n. So we need to take the sum from n is 1 to infinity of each of these. So there's an infinite number of linearly independent functions, and each of them could be multiplied by a constant, and they would still be a solution. So instead of just adding 2 together like we had up here, these were 2 linearly independent solutions. It turns out that there's now an infinite number of them, and they each have a number in front of them. Okay, so this starts to look like it would be impossible, but there is hope. Okay, so we need to sum up all the ones from 1 to infinity. Each of them has some number, some coefficient in front of them that we're going to call a sub n. It's associated with that one, and then it's times sine of n pi x over L times e to the minus n squared pi squared over L squared dt. Okay, so our last task here, you see that our a, before we had an a up here, and now it becomes a sub n. So what we need to do is to use our last boundary condition. So our initial condition. So initial condition, we have c at t is equal to 0, and so again, we've got this infinite series of products of sine and exponential functions with a constant we don't even know. It seems impossible, but it's not. Okay, so looking at the initial condition now, our last thing, c at t is equal to 0 has to be equal to the sum from n equals 1 to infinity of a sub n times sine of n pi x over L times e to the 0. Okay, which this is just becomes 1, right? And so this is called a Fourier series, and it's named after Joseph Fourier, who discovered it. And so what this is it's a function that is the sum of all these different possible values inside the sign here from 1 to infinity times some constant. And you can actually figure out what the values of a sub n need to be. You can write down an equation for them as a function of n using the techniques that are used to develop Fourier series. And it turns out that these Fourier series can be used to build any function over a finite interval. Okay, and so they're often used to look at like a square wave. In electrical engineering, they use a lot of these Fourier series for analyzing time series data and things. But so you can actually create, instead of a sine function that has a curve like this, you can make one that's a square that goes up and down. And that's actually kind of the one that we're going to be looking at here. Okay, so so we need to now figure out the values of a sub n, and then we have the last piece here of our equation. And then once we have the equation, we can look at how to work with it. Okay, so in the next video, I will talk about how to get the values of a sub n for this Fourier series.